Yeah, welcome back to my work on Riemann's zeta functions, Riemann's hypothesis, and many more. So we just finished the proof of Riemann hypothesis from different angles, three different ways we proved, all excluding the induction approach one, with which that count will be almost total four. So now we are just when we are analyzing the result, I just got a similarity with Cantor's theory. Zeta minus 1, which give us a half, whereas zeta 1 give us a greater value. How can it be possible? That was the question I faced, but I was not finding any relevant answers. When I encounter with this Cantor's theory, then I find the rational behind this, because all the rational numbers can have multiple representations. So are they are although they are countable also, like the integers, but integer has got a unique representation. So their densities are little small. Qualitatively their density, their uh, total weightage is little lesser than the um, rational numbers. This way actually it matches the Cantor's theorem, which gave that countability, there are countable infinities are lesser than uncountable infinities, which he encountered in a similar kind of thing related to irrational numbers. So he proved it for irrationals, and this one proves for rational numbers also. Rational number versus integers, natural numbers. So okay. hmm. Now zeta results confirm prime number theorem. Prime number theorem, anybody who have start with number theory, so he tries to prove prime number theorem. So I thought I will also do that, but once I try to enter there, then I see it's kind of a obvious thing to do. So just put some let me put some a few words. Let me inject a new concept that itself will be sufficient to explain why it is a kind of obvious thing. So we have seen that uh, we know that prime number theorem talks about primes and gives the scale. We can find the primes, number of primes. It's the natural logarithm scale. So up to a given number, to get the number of primes, we can have an estimate based on the it's that number divided by ln upon ln of n. So which give a rough estimate, and almost it is verified to a huge numbers, and this prime number theorem works, and it is also proved. I think from the zeta functions work itself, Delahaye, Poussey and Hadamard has proved it. So I am not going to in that area, but just to share my view, because it has got a connection with natural logarithm, so it should be something related to E, the Euler's constant, or sorry, Euler's number, I think. Yeah, mathematical constant named Euler number also, which is represented as this formula limit n tends to infinity 1 plus 1 upon n whole to the power n. So this is a calculus thing which was invented long before calculus and used in logarithm. Now my point is that if we, instead of writing 1 here, if we write 2 here, then also we are going to get the same result, because 2 is also a kind of unity. That's why we got the zeros in half line. 2 2 is kind of a unity concept, in the sense, because when it is multiplied with half, that gives unity, and half is kind of a base of the all bases, because that's the smallest part of unity. So behind e, there is also one more a complex kind of base. On the real number line, we can see that has got a connection to e, but there are some complex issues involved with this, which we will come to know when we enter into the complex logarithm, and the other part of this piece of mathematical work. So now the point is that we can, both the form is equally good. That's my point. Also I got this similar to fundamental theorem of arithmetic. I got one more representation, fundamental, which can be uh, called as fundamental theorem of numbers. We know numbers numbers are basically composed of prime factors, but here it's a different story actually. Primes product can be equals to double of sum of numbers. That is also kind of true in our logical sense, common sense also. But I have got a induction proof of induction, how I derived this from the zeta results I got. It's just a few manipulations from side, and then handling the infinities little bit. That's it. Now the redefinition part, first we will try to remove the poles, remove the zeros, trivial zeros, um, using this representation of gamma function. Gamma of 1 minus s multiplied by gamma of s is equal to pi by sine pi s, because in the functional equation of Riemann, when if we put this, then we can get one more relationship coming out of this in the cos form, which then we will be able, it will enable us to remove the zeros into some more meaningful thing. It although it will be also it will have some other linkages to other zeta functions, zeta odd values, zeta 3, zeta 5, zeta 7, zeta 9, but still it will be have a better meaning, and it is a better continuation of better continual representation of zeta function. Then this I have done on the Riemann's original equation itself. I have not tried the harmonic one. Now I will be doing the same thing on the harmonic one. So here it will give me these values, zeta minus 1, zeta minus 3, zeta minus 5. In the normal way, the values are half, minus 1 upon 6, plus 1 upon 6, minus 3 upon 10. So here there is a alternate sign change here happening here. Now if I replace the sign with cos, and in that representation, just similar to gamma's the alternate gamma representation, we can get the same thing, and this time we will be getting the all the even negative numbers, zeta minus 2, zeta minus 4, these will be equivalent to zeta 3 by pi square, zeta 5 by pi to pi to the power 4. Only the it is similar to the Riemann's original one, but the coefficients are different, so the values are different. This part I will be coming last, because here we don't have to do much. Okay, let us do this, finish this. Proof of Hodge conjecture, actually it talks about a lot of things which even I am not an expert in that, but somehow when I read about the this problem statement, I saw some connection with zeta function. Only that part I will tell you. I cannot tell you the total. I will take you. This is a copy pasted thing from Wikipedia, taken from Wikipedia, that I have disclosed in the. Okay. Let me. There are topology here. Then complex projection is there. Algebraic variety is there. Hodge class, group theory. Everything is there. But ultimately, it gets stuck in an issue called number theory, because here what Hodge has expressed, that he has got some doubt. He is doubting that on the higher dimensions, although it's even dimension, even number of dimensions, if we go higher, high and high, so whether there is a dead end or not, because as, at some point of time we may have a feel that okay, math doesn't work anymore. So will we encounter that kind of situation? And to prove that he was wrong, no, he only assumed, so he was right, that no, it will not break. The basic algebra will remain same. So what we have to do, that we have to see, to prove that every Hodge class X is a linear combination coefficients of the cohomology classes of complex subarrays. We just need to check the compliance with addition laws and the scalar multiplication laws. So zeta function has given us a form which give um, which is very equally good for any number of dimensions we climb up, because in number theory, if you say there is only one number, it's 2. All other numbers are actually byproduct of this number 2. Parallel plus 1, when we are doing plus 1 plus 1 plus 1, that means um, we are just creating more and more dimensions. So whatever dimensions we climb up, because the zeta function has got analytical continuation, and the at unit level it is working fine. It has got these basic properties of algebra, like additive inverse in the form of zeta, zeta minus 1 plus zeta of 0 is equal to 0. Then there is multiplicative inverse, 2 into zeta minus 1 is equal to 1. So this kind of thing is there. So um, linearity will not be in stake. It will be always it will be true. So as many dimension we climb up, it will be always true. So mathematics will continue as it is, at whatever level we can go, and Hodge conjecture will be true. And for the I have, towards the end of the work, actually I have derived some complex logarithm kind of formulas, which I have shown here on the a big number representation called arrow notation. So we will come to know about this. Basically it gives the ln of this kind of big numbers with negative numbers, it will give an additive inverse of 0, and it will be the inverse also. It can be sometimes plus and minuses can go a double of minus. That also will happen in case of subtraction. A double of the thing, when you subtract we get the double of the thing. That will happen here. Then dividing will give us -1, a kind of uh, multiplicative inverse unit. Then this will go, the when you product this, then it will go the square of the same number with a minus sign in front. So this kind of algebra will be possible at n number of at 2n number of any dimensions. So that's the reason why Hodge conjecture will be true. Proof of BSD conjecture. It's a conjecture given by Bartsch, Nathan, and it's about elliptic curves. Actually, it is about the rank of the sum from here is a statement: let E be an elliptic curve over Q, then E has got good reduction at all primes P not dividing n, and it has multiplicative reduction at the primes P that exactly divide by n, and it has additive reduction elsewhere. Here I use this concept of Hasse-Weil, and he actually targeted this problem, same problem with the zeta function. Then also some L function is there involved. So now to prove for this proof to happen, zeta of 1 has to go 1, then only the rank will be coming asymptotically to 1. So from this, if we set this whole thing into side, if we take the zeta of S is equal to yes, we need to do little bit of change. Then in this form, because we can, if we plug S is equal to 0, then it will be minus half, and on the bottom it will be plus half. This one, and -1 is still 1. So that will be the reason why these elliptic curves will have a rank of 1 unit rank. Reasons for yes, P versus N problem also I could try, but I didn't give a try because I think lots of security questions are involved with this, so I don't want to be in a situation where I may be questioned. People remember me for doing something hacking kind of thing, so I don't want to be a hacker. I didn't give it tries, but honestly speaking, it's crackable. It's PA versus NQ. The RSA algorithm, we know it's related to primes, so RSA algorithm is quite invincible. With the right direction, it can be right motive, right strategy, we can bring out some anti RSA type algorithm to break the prime security security. Now twin prime conjecture. Actually, as I said, this 2 is a kind of uh, unit concept. So that is the reason all these prime conjectures, small conjectures we will be talking about, like twin prime, Goldbach conjecture, all these are following follows from this one new novel concept of unity. Still, to give a formal proof that we can derive this proof from the prime number itself, PNT, prime number theorem itself. So let us think this prime number limit, whatever it gives, the n upon ln of n. Let us think a prime close to that value. Then we take the double of that number, 2n. Then if we take the log with respect to this n upon 2n, it is obvious that the log will be more than 2, or some case it may be 2, but it will at any point of time, for any number it will not go below 2. That's the reason actually twin prime is guaranteed, is after infinity. After infinity, the twin primes will be appearing again and again, again and again. Similar case happens Goldbach's conjecture also. Here, what we have done, I have taken a big number, then I have taken the sum of all the natural numbers up to that number, then I have doubled it. Then the formula will be coming around n into n plus 1. Then if we take the log with respect to the determining factor of PNT, the result will be giving us the limit of lower boundary of the representation from representation of Goldbach partitions, and that will be greater than 2. So actually Goldbach's strong conjecture is about all this, that we need to just prove that it is 2. It can be equal to 2, even sometimes it is more than 2. Those cases we know, but the proof is required for 2 only. So immediately it follows from the strong version to the weak version also, that an even number can be written in sum of 2 prime form, and an odd number can be written as sum of 3 primes. Legendre's conjecture, it talks about there will be always a prime number between n square and n plus 1 square. Here also the strategy is same. We have taken a big number n, then we have we have taken the sum of all the squares up to that number, and we have doubled it. The quantity will come like something like this: n into n plus 1 into 2n plus 1 upon 3. So now if we just n to be replaced with the n plus 1, then we will get one more representation. Now the difference will be, now if we take the log of both these terms with respect to n upon ln n, then we will get the lower bound of the number of primes which may appear between these two successive squares, and eventually we see that the bound cannot go lesser than 1, as both uh, just there is a common number which will get reduced, but the second number being the higher one, it will always have a difference of 1. Sophie-Germain prime conjecture, which talks about the pattern of primes, that there will always be a prime of 2p plus 1 form. So once we have 2p plus 1 form, so if we take uh, p and another prime 2p plus 1, so what will be the gap? The gap will be around p plus 1. Now we have proved the twin prime theorem. That was the bound in that case was 2, and here it is p plus 1. So in that case it is similar to the twin prime or polygonal prime conjectures. So it's not a different kind of thing, it's the same story happening here also. Landau's prime conjecture, which talks about the infinitude of many primes numbers of the form n square plus 1. N square plus 1. Yes, we will be doing the same thing with what we did in Legendre's conjecture. We will take the a big number n, then we will take the square of all the natural numbers up to that n, we will add up and we will multiply by 2 the end result. Then we will be comparing the limit to this, and the result will be give us the lower bound, which is always about 2 plus. So because our twin prime bound is 2, so this form is also guaranteed. Broca's prime conjecture, which talks about the number of primes between two successive number square. No, it's 2 successive prime number square. It should be greater than 3. That means actually he is asking for 4 primes between 2 consecutive prime square. So what we see in the twin prime case, that there is the bound is 2 always. So if we square that up, because we are taking the gap between 2 primes, successive primes, so the bound should also be squared up in that sense. So we will have at least 4 primes between 2 successive prime squares. Opperman's conjecture also same thing, which has got a 2 part actually. There is a prime between x square and x into x plus 1, and there is a prime between x square minus x and x square. We have taken the same approach. We have taken a big number n, then we have taken the square formula, then we found the gap, compared these two representation. One is x square and one is x square plus x. Both the cases it succeeds. Collard's conjecture. So here it's a game kind of thing. which starts with the any random number, and collage has prescribed some operations, two different operations or two different kind of numbers. If it is odd, it should be multiplied by 3 and subsequently added to 1, and if it is even, it should be straightaway halved. And this in these operations on any random number will ultimately end up in n, in end up in 1. That's the conjecture is all about. So here we need to see, to prove this kind of conjecture, we need to see the 2 and 3, how it is related to the numbers. I'll explain this with the rotation around the unit circle. Suppose, yeah, for unit circle we have the axis is, we put x-axis, y-axis on a pi by 2 angle, and our complete cycle rotation is taken as 2 pi rotation. So complete cycle. Now in the pi by 3 notation also, it will sometimes at 4 points it will match, coincide with the rotation also. Suppose 30, 60, 90, if we go, so it will meet the axis at 90, at 180, at 240, and at 360. 4 places it meeting, and one complete cycle is, in the next cycle also it will do the same thing, it will keep on rotating. So this this kind of operation, Coulom's prescribed operation, if need to be finished, then either it may happen two cases. The outcome may happen, it may go either to infinity, or it may end stuck somewhere in the loop in between. But with the other numbers it may happen so. But 2 and 3, if because they are co-moving along the same unit circle, so for infinity, up to infinity also they will do the same thing, and eventually this game will be ended in 1, because whenever even number of the form 2 to the power n is encountered, the game will start decline to 1. It's a trivial theorem actually, but if you try some hard proof, you will be more puzzled. As hard you go to try it, it will get more puzzled, more and more puzzled. It's better to try this simple approach of induction. Okay, let's stop here.